Okay, so welcome everyone to this new Graviticulas seminar session. Today the speaker is Pablo Martinez. Pablo did his bachelor degree and master's degree in Universidad de Valencia. Right now he's doing his PhD in IFIC Institute, Centro Mixto de la Universidad de Valencia y CSIC. I hope I did it. I say it okay. And he is right now a visitor student in the Max Planck Institute in Heidelberg, Germany. So Pablo, many thanks for giving this seminar today, and please go ahead, just share your screen.
Okay. So you should be seeing it now?
Yes, perfect.
Okay, that's great. So first of all, thank you for inviting me, and it's really a pleasure to give this seminar. Also, before I start, I also want to thank some of my collaborators because the work I'm presenting here is based on things we did together. So thanks, Pablo, Stefano, Susana, Sergio, and Mariam. And so the topic I'll be discussing is terrestrial and cosmological approach of non-standard neutrino interactions. I also want to ask you if you have any questions. I will make some stops in case there are some questions, and you can also interrupt me if something's not clear. I think it's better if you just stop me and ask for the question. It might be faster sometimes. So yeah, this is basically the outline of the talk. I would start with a short introduction to neutrino oscillations, just to show a bit where do we stand. And to summarize with one word, we are entering precision. And this means that we can actually start searching for beyond the standard model physics in neutrino oscillations. And one of the things we can look for are neutrino non-standard interactions. So after that, I will just shortly introduce the formalism, and I will move on to discuss two works this talk will be based on. So the first one will be non-standard interactions with quarks, and we will see how future solar neutrino experiments can actually, solar and reactor neutrino experiments can bound non-standard interactions with quarks. And then we'll move to non-standard interactions with electrons and address this from a cosmology point of view. And I will just end up with some remarks about this. So just to warm up, neutrino oscillations is a well-known quantum phenomenon that has a dependence of L over E, where L is the baseline of the experiment and E is the energy of the neutrinos. The overall phenomenon can be parameterized with 3 mixing angles, 1 phase, and 2 mass splittings. And it's been extensively tested with different sources for different baselines at different energies, and also for both neutrinos and antineutrinos. And so it's a very well understood phenomena, and the framework is also well established. I say so because different experiments measure different parameters, and they all show a good agreement. And so what we're doing now is we're combining the results from these different experiments to actually have better measurements of the oscillation parameters. And with that, we're reaching actually precision. So I'm showing here the results of some of this global phase 2 neutrino data. So this is actually taken from this reference here, which is the FIT we do in Valencia, but you can also check some other groups that also do that. And so this is the chi-square profiles for the 6 oscillation parameters. So I want you to notice that 3 of them, so 2 of the mixing angles and 1 of the mass splittings, are measured with great precision. And the remaining 3 oscillation parameters are also well measured, but there's still some unknowns related to them. So the first one is for 1 of the mixing angles, we don't know the octant. That is, we don't know if the best value is larger than 0.5 or smaller than 0.5. So that is something that future experiments are going to address. And this can be interesting from a model building perspective. Another of the unknowns is the ordering. So you can see here, I'm plotting the mass splitting at the absolute value. So actually, this mass splitting can be either positive or negative. So if it's positive, M1 would be the lightest neutrino, or what we call M1 would be the lightest neutrino, otherwise it would. Okay, so we know the value in case it's normal ordering, we know the value in case it's inverted ordering, but we don't know which is the right order. And this is also something that's going to be addressed in the future. And finally, regarding the CP violating phase, we are starting to have some hints about its value, but still not unclear. And this is where this is the largest unknown we have in the picture right now. But I don't want you to miss the perspective. We are doing precision physics. I'm showing this here in a different way. So you can see this is the 1 sigma error, like the percentage of the 1 sigma error in the oscillation parameters. So you can see for all of the cases, so for the 2 mass splittings and for the 3 mixing angles, they are measured at 1 sigma level with precision that's below 5% or 5% in the worst case, except for the CP phase that, as I said, it's, well, still a bit tricky, but also current and future experiments are getting better at this. And definitely with future experiments, this will improve. So you see, we're talking about percentage level deviation. That means that we can also start looking for percentage level effects from the understanding model physics. And since in the future, these measurements are going to improve further, we will also be sensitive to smaller deviations from this picture. And this is what this whole talk is about. So I'll be discussing neutrino non-standard interactions. And here I will do just like a short introduction for the formal lesson. If you're interested in a review, you can find it here. And the interest in neutrino non-standard interactions comes from the fact that they can arise in many standard model extensions, including some of the ones that try to account for neutrino masses. So what we generally do is we study them in terms of effective field theories, and we parameterize this additional interactions of neutrinos with fermions through 4 fermion operators. So from now on, I will be just focusing on neutral current non-standard interactions, and we parameterize this with this general Lagrangian here, which you can see this is a 4 fermion operator. So we have 2 neutrinos that can in principle have different flavors, so alpha and beta are the flavors of the neutrino. Then these interactions can be with different matter fields, and I will be considering electron up and down quarks. And in principle, we can also have quark paralysis. And I want you to notice that I have introduced this coefficient here. So this dimensionless coefficient is a way to quantify how strong these new interactions are with respect to the standard model. So if this is order 1, this means that this is just order 2 square root of 2 G Fermi, and this is the strength of standard model interactions. So basically, if this coefficient is of order 1, it means our new physics is as large as standard model. But they can also in principle be smaller or larger, but probably you would have seen that already. And another important remark at this point is that we can classify these coefficients in 2 categories. So the first one is non-universal NSI that corresponds to the situation in which we have both neutrino flows with the same flavor. And they're called non-universal because if they're different from the differences between them are different from 0, it means that not all neutrinos interact in the same way, with the strength of the interaction is not the same for the 3 flavors, and that breaks universality. And then we can also have interactions in principle in which the flavor of the neutrino is different, so that's why they call flavor changing non-standard interactions. So in the case of scattering, for instance, this would correspond to, for instance, an electron neutrino scattering or some electron or quark, and then turning into a neutrino of a different flavor. So in principle, this is not allowed in standard model, but you can actually extend it in a way that it is. And how can we prove this neutral carbon non-standard interactions? Probably the first thing we think about is doing some scattering. So for a certain process, we know the cross-section that's predicted in the standard model. And so we can see if our data agrees with that or not. And we can see whether adding extra interactions of neutrinos can give a better fit or a worse fit. So let's take an example, for instance, neutrino electron scattering. So we bombard some electrons with a beam of neutrinos, and we see if we say we have some new non-standard interaction and see whether the cross-section agrees or not. And from this, we can derive bounds on non-standard interaction parameters. We can also do that, for instance, with coherent elastic neutrino nucleus scattering, and so on. Another way to do this is with neutrino oscillation experiments. So we know neutrinos are sensitive to the matter when they propagate in matter. They're sensitive to this because along the way they forward scatter of electrons and quarks, and this can modify the propagation of neutrinos. So if we have additional interactions of these neutrinos with electrons and quarks, then the oscillation probability that we predict is different. In searching for these deviations that we predict in the presence of NSI, we can again set bounds on non-standard interactions. Here, there's something that's a bit tricky. In the end, at the end of a neutrino oscillation experiment, there's always a vector. That means that we also have to take into account the fact that non-standard interactions alter the detection process in some cases. So we will also discuss this. A third way that you might not have think about looking for these non-standard interactions is from cosmology. So we know neutrinos play an important role in some moments of the early universe. In particular, we can learn about non-standard interactions from the decoupling of neutrinos from terrestrial plasma. And this is what I'm going to discuss in the second part of the talk. And finally, in some very particular cases, we can also get information on non-standard interactions from colliders. So for instance, at lab, looking at electron-positron going to two neutrinos plus a photon, we can study non-standard interactions with electrons. So we've got quite a lot of different ways to look for the signatures. And as I said, what this seminar is going to be about is divided into parts. So the first part is non-standard interactions with quarks, and we will address that from the point of view of neutrino oscillation experiments looking at the solar sector. So we will discuss JUNO and Hyper-Kamiokande and what will they teach us about non-standard interactions. And in the second part, I will discuss the lessons we can learn from non-standard interactions from cosmology. And in this case, it will be non-standard interactions with electrons. So I hope the stage is clear at this point, and I will start discussing the first part. So non-standard interactions with quarks from the future of the solar sector. I want to thank at this point Susanna and Marian, because this part is based on work we did together, and that you can find here the preprint in case you're interested. And I want to start with a spoiler. This is the take-home message of this part. What I'm going to try to convince you about is that combining two different experiments, such as JUNO and Hyper-Kamiokande, will allow us to simultaneously have a very good measurement of the oscillation parameters, much better than one we have currently. And simultaneously, we'll also be setting strong bounds on NSI. So we will have both of the things just from the combination of these two experiments. So I'm going to show you how and why. So as I said, in oscillation experiments, the propagation is altered because neutrinos interact with matter. And if we have additional interactions, we have to take them into account. So the Hamiltonian that rules the dynamic of the system has a vacuum term. So this is just standard oscillations in vacuum. Then we have a second term that accounts for standard model interactions. And then we have an additional term that we have to include because along propagation, from the source to the detector, neutrinos interact with the matter field, so electron up quarks and down quarks. So you can see here in this effective potential in the diagonal, we have what I introduced before as non-universal NSI. In the off-diagonal terms, we have flavor-changing NSI. And you can see this flavor-changing NSI are not present in the case of the standard. I also want to draw your attention to the fact that I'm showing here epsilon with a super index P. That means it's the vector component of the interaction, because this one is the only one that affects propagation. So before I was expressing non-standard interactions in terms of chirality. Here I'm expressing them in terms of their vector axial components. So the axial component does not modify the propagation, but the vector component does. And that's why it's introduced here this way. And I also want you to look at the fact that the interaction depends on the number density of the matter field, so on the number density of electrons, up quarks and down quarks. And this means the effect is not going to be the same in a very dense environment or in a not so dense environment. So for instance, it's not going to be the same on the sun or on Earth. Also because the composition on electron up and down quarks is different. So we're going to be playing with all these ingredients. And as I said, the tricky thing about non-standard interactions is that they modify the propagation, how neutrinos propagate, and this can manifest in deviations on the oscillation probabilities that we expect. And from not seeing these deviations, we set bounds. A side comment here, it might be interesting for you to know also that non-standard interactions can provide additional sources of CP violation, and this has been discussed in the light of some tension between some neutrino oscillations experiments measuring delta CP, so between two recent results from T2K and NOVA. And this is also interesting when it comes to sources of CP violation, in case you want to do some asymmetries in the early universe. And finally, as I said, non-standard interactions do not only modify the propagation, but also the detection process. So for instance, if we consider non-standard interactions with electrons, and we're using elastic scattering of neutrinos on electrons for detecting these neutrinos in our oscillation experiments, then non-standard interactions with electrons affect the propagation, but also the detection process. And this can make the analysis quite complicated. Okay, so just for you to have in mind that in some cases, non-standard interactions in oscillation experiments can get really, really complicated and quite messy as well. So let's talk about solar neutrinos. I'm showing here a picture that I think summarizes quite well the physics of solar neutrinos. So on the y-axis, you can see the probability of survival probability of electron neutrinos. So neutrinos are produced as electron neutrinos in the sun. And this is the probability that we find an electron neutrino on Earth. So at low energies around here, also before I comment on that, the blue line corresponds to one choice of oscillation parameters. The red one corresponds to a different one. So we can just focus on one of them if you want, on the blue one, for instance. And so the solid line also is referring to the neutrinos that come from the sky. So that just directly go across the atmosphere and reach the detector, whereas the ones that we refer to as night are the ones that go through the Earth. Again, we will see what this is important. So at low energies, for energies below 1 MeV, the physics is dominated by vacuum oscillations, basically. But when we move to higher energies, matter effects in the sun start being relevant, and they actually give rise to this transition region. Also, so if at these energies standard matter effects are important, one can expect that at those energies non-standard interactions will also start to show up. Another thing is that you can see, I told you, solid line is the neutrinos that come directly, whereas the dashed line are the ones that go across the Earth. And we see there's a difference here for very high energies, very high energies for solar neutrinos, so around 10 MeV or so. This is due to the fact that the neutrinos that go across the Earth also feel matter effects on Earth. So again, this asymmetry between day and night can also give us a hint of matter effects. And if we have non-standard interactions, they could also show up in this asymmetry. Okay, so what we want to study is rather large energies and also the asymmetry between day and night. And a final comment, this picture of solar neutrinos is currently quite well established, or very well established by the measurements that XENO perform at low energies, and also, so you can see here the data points, and you can also see for higher energies, the data from Hyper-Kamiokande and SNO that kind of quantitatively and qualitatively agree quite well with what we expect. There's one thing that makes our life easier when it comes to solar neutrinos, and it's that it is possible to describe it in terms of 2 neutrino oscillations rather than 3 in some cases. So that's the case for us. So the probability, survival probability of electroneutrinos is related to the survival probability in case of 2 neutrinos only. And in that case, we can simplify our Hamiltonian to have this form. So again, we have the vacuum term, another term that accounts for standard model matter effects, and then again this non-standard interaction potential. You may notice that here the coefficients are not the same ones. So I'm calling epsilon prime to the one that's here in the diagonal, and then epsilon to the ones that are off diagonal. Okay, and these are some effective NSI parameters that just a complicated combination of the epsilons I just showed before. So from now on, I will be working with this effective NSI parameter. So just to make it clear, epsilon prime is in the diagonal, epsilon is off diagonal, and they also quite related to whether they're non-universal favor change. And so I said the current status of solar neutrinos is that we have a good understanding of the picture, but we also want to do more precision measurements. And that's one of the goals of Hyper-Kamiokande. So it is a water triangle detector that's going to have a quite low energy threshold. So 3.5 MeV in principle could be achieved. That means we're going to be sensitive to all the region where matter effects are relevant for solar neutrinos. It is also expected to have 8 times larger volume than Hyper-Kamiokande. So this is going to give us much more statistics. And for the detection of neutrinos, it uses elastic neutrino electron scattering. So it's this process here, and it's sensitive to all neutrino flavors. So I told you we're going to be focused on neutral current, non-standard interactions with quarks. So this is good. We're using a neutral current process, but it involves the scattering of neutrinos with electrons. So non-standard interactions with quarks are not going to change this. So we don't have to worry about any modifications in the cross-section. Non-standard interactions with quarks will only modify propagation in the sun, but not our detection. And what we did here was we decided to perform an analysis that taking into account the spectral shape for day, but also for night, so that we could have all the information on this asymmetry I told you about between the neutrinos that come directly with respect to those that go through the Earth. We also included a lot of systematics in flux, the shape, the normalization, the energy scale, the energy resolution in order to make our analysis as realistic as possible. We also discussed the possibility of what if we don't measure such low energy neutrinos, but other energies, or like if we had a second tank as large as this one, would it improve a lot or not? So the main idea here was to have quite a realistic study. And we also focused for simplicity, we just focus on quarks. So in principle, one can consider T quarks or up quarks, or non-standard interactions with T quarks, up quarks, both. So we decided to limit ourselves to just T quarks, just because we had to make some simplifying assumption, but in principle, the results are general as well. And so in the absence of NSI, this is what we can expect from Hyper-Kamiokande. So this is the 1 sigma, 2 sigma, 3 sigma confidence level contours for the oscillation parameters delta and square to 1 and sine square theta 1 2. So you can see the mass splitting is measured relatively well. It's less than an order of magnitude at 3 sigma level. So for solar neutrinos, this is a very good measurement. And also the mixing angle is determined with quite good accuracy, better than the one we have currently almost. So this is actually a very good measurement that we can expect from Hyper-Kamiokande. But what happens if we include additional parameters such as NSI? Well, the thing gets quite complicated. I want you to focus on the left panel now. So here what we're doing is showing the confidence level that Hyper-Kamiokande would determine if we allowed to have one non-zero NSI parameter, so in this case epsilon, and we set the other to 0. So we can only have off-diagonal contributions. And so you can see that the precision with which Hyper-Kamiokande can determine the oscillation parameters is worsened like incredibly. Now the mass splitting spans over 2 orders of magnitude. And you can also see that it's even consistent with non-oscillation, so 0 mixing angle. So really, if we add this extra parameter, Hyper-Kamiokande is not going to give. If we try to make an analysis of Hyper-Kamiokande with non-standard interactions, we're not going to be able to learn anything. Also, now we can do the reverse exercise. We just set the other parameter, the epsilon to 0, and we allow the variety of the parameter. And so you can see again that there's large degeneracy with the mass splitting, and we also get a degenerate solution for a very different mixing angle that's normally called the LME dark solution. So the idea here is Hyper-Kamiokande on its own cannot. If we try to learn something about NSI from Hyper-Kamiokande only, we're going to learn nothing about oscillations nor about NSI. So we need to do something about it. The idea is to combine this with some other experiment that can give us complementary information. And the sort of experiments that that complement quite well solar neutrinos are long and medium baseline reactor experiments. So you probably have heard of CAMLAND, who is a long baseline reactor experiment that measured reactor neutrinos from different reactors that were approximately 180 meters away from the detector. And the good thing is, or the interesting thing is that it measured the same oscillation parameters as solar neutrinos. So you can see here what CAMLAND reported in 2008. The color regions are the results from CAMLAND in terms of the mass splitting and the mixing angle. And these contours here are the results from solar neutrinos. So you can see solar neutrinos determine very well the mixing angle and not so well the mass splitting, whereas CAMLAND has a very accurate measurement of the mass splitting, but not so good about the mixing angle. And so combining both of them, you actually get a nice allowed region for the parameters that's around here. Okay, so this is the complementarity. We're also looking in the future between Hyper-Kamiokande and in this case, JUNO. So JUNO is what we call a medium baseline reactor experiment because it sits at 50 kilometers from the reactors. So it's not as far as CAMLAND, which is approximately 200 kilometers, 180 kilometers. And short baseline reactors are just 1 kilometer. The detector is 1 kilometer away from the reactor. So it's something in the middle, it's 50 kilometers, we call it medium baseline. And JUNO is gonna try to improve this measurement considerably, even incredibly. So it's a 20 kiloton lipid scintillator that is like factor 20 larger than CAMLAND. As I said, it's the detector is 50 kilometers away from the reactors, and for the detection, it uses inverse beta decay. So this is a charged current process, and so neutral current and SI do not modify this. You don't even need to worry about the cross section. We can study non-standard interactions, no problem. And it's very large, so we expect incredibly good statistics. And it's aiming for an incredibly good energy resolution. So in principle, one can learn a lot of physics from it. And it's trying to determine the two mixing oscillation parameters from the solar sector, but also these other two. So the other mass splitting, theta 1,3, and the mass hierarchy. So it's a very, very ambitious experiment. And one last comment that we need to know about JUNO is that the baseline is rather short and matter effects are not very relevant. So if matter effects are not relevant, then NSI are also, we cannot expect a huge impact from non-zero NSI. But still, JUNO is really aiming to do such precision measurements that all these small effects can actually play a role. And this is something I find quite nice. So what we did, we simulated JUNO. JUNO requires a 3 neutrino description, so we cannot do this to a neutrino simplification we did for solar. But since we're going to do NSI, what we did is we just chose two non-standard parameters, epsilon tau tau and epsilon EE, and we mapped this into the effective parameters that we're going to use, so epsilon prime and epsilon. So this is just a simple relation between them. And we simulated, we did a simulation of JUNO taking into account all the systematics that the collaboration is taking into account. So the errors in the flags from the reactors, the fission fractions, some expectoral errors as well. So also we try to be as realistic as possible at this point. And this is what JUNO expects to measure in the absence of NSI. So you see for the mass splitting is a very precise measurement. I mean, it's not even it's like smaller than 1% accuracy in the measurement of the mass splitting and also in the measurement of the mixing angle. I mean, it's a very, very precise measurement that they're aiming to. But again, if we include NSI in the analysis, or if we try to learn something about NSI from JUNO only, the things are not so good. So again, this is a similar figure to the one I showed for Hyper-Kamiokande, but this one is for JUNO. Here you can see how epsilon enlarges the confidence contours that we obtain for JUNO. So for having epsilon prime equal to 0, you see there's a large degeneracy with mass splitting that will now be not so well determined. Whereas if we fix epsilon to 0 and we allow epsilon prime to be non-zero, we get a much worse determination of the mixing angle. And if you allow both of them to be non-zero, then you can imagine that the confidence regions will span both like this and the horizontal direction as well. So definitely non-standard. If one tries to fit oscillations and non-standard interactions at the same time in JUNO, one definitely does not get good bounds on NSI nor on the oscillation parameters, or at least not so good on the oscillation parameters. It will still be very nice determination of the oscillation parameters, but they will not reach the accuracy they want. So just to summarize the status is that JUNO can measure oscillations very precisely, but it is not very sensitive to NSI because matter effects and NSI are not very relevant for JUNO. Whereas in Hyper-Kamiokande, the measurement of the oscillation parameters is not so good, but is very sensitive to non-standard interactions. So they can nicely complement each other in this case, and this is what we did. So we combine both analysis, and this is what we get. So let's have a closer look at the two sets of parameters. So for the oscillation parameters, you can see here are results. So a combination of Hyper-Kamiokande and JUNO allows to determine at 90% confidence level both the mass splitting and the mixing angle with a 1% precision. So you might be interested in the numbers. Otherwise, it's not that relevant. But you see the mixing angle is well determined. It's 0.32 with a small error, and also the mass splitting is just, one would know it's around 7.5 plus minus 0.1 10 to the minus 5. So it's again a great measurement. Even if we account for NSI. Sorry. And when it comes to non-standard interactions, this combination is also quite good at setting bounds. So these are the bounds we obtain at 90% confidence level. So they're around 0.1. That means that this combination can bound non-standard interactions to be smaller than a 10% of the strength of the standard model interactions. And I think the fact that it's coming only from 2 oscillation experiments this is quite outstanding. So I hope you get the whole idea of this work we did. That JUNO and Hyper-Kamiokande can complement them each other very nicely. This is illustrated also here. So these are the remaining projections that I wasn't showing. You can just see that confidence regions for JUNO are in pink, for Hyper-Kamiokande are in purple. And you can see that the results we were obtaining are because in many of the cases, the values that are allowed for JUNO and for Kamiokande are in different directions in the parameter space, so that that makes them really nicely complementary. If anyone's interested, we can discuss this further. I think it's the idea is here, I hope. And so the take-home message that I want you to have from this part is that when it comes to non-standard interactions with quarks, in future, JUNO and Hyper-Kamiokande are going to both give us good measurements or good bounds on non-standard interactions, and also a really accurate determination of the oscillation parameters. So they're going to improve what we have now in terms of oscillations, and even if we allow for NSIs in the analysis. So this is really very impressive. And a last comment for this, I just show everything for deep quarks in case one wants to consider up quarks. And then the only difference is that since the number density of Q quarks and D quarks is different both on Sun and on Earth, then one has to adjust the potentials accordingly. But the overall physics is the same. Like the overall thing is the same, and that's what we just show for the quarks. So maybe I can stop here and take some questions, and otherwise I can move on to the second part. So I don't know if there are any questions. I don't know if I'm alone or there's someone else.
No, we are here.
Okay.
Okay. Is there any question at this point?
Or otherwise,
Diego raised his hand.
Yeah. So thank you very much for the first part of your presentation. So I have a couple of questions. So NSI can have, as you mentioned, can affect propagation and detection, but they can affect as well production. The effect they generate in production is small, but as far as I can see, you're looking to 1% effects. So how much can you justify ignoring production effects, given that the effects you are looking at are of the same size that the production in NSI is?
The thing is that production happens through charge current processes, right? But we're just considering non-standard interactions with a neutral current process. So when you do only neutral current non-standard interactions, the production is not affected. It's only when you do charge current non-standard interactions that you have to account for the effects on production.
Okay, so your assumption is that you only have
neutral current.
NSI is only affecting the neutral sector.
Yeah.
Okay. Another comment that I have is, so I understand that since you are looking for 1% effect, so you are relying on a 3-flavor scheme rather than a 2-flavor scheme, right?
Yeah.
Okay. You didn't mention about the statistical analysis that you did, but since you were showing chi-square distributions, I guess that you are sticking to the Wilks theorem. So you are assuming that your data is distributed according to a chi-square function. There are instances in which this is not the case. For example, when you look to sterile neutrinos. So how much how robust are the results based on a chi-square distribution are in this case, in particular for Hyper-Kamiokande?
I mean, I'm not 100% sure. I think it's quite a reasonable assumption from the moment that we're just doing projected sensitivities, that we're not actually performing the full analysis of the data. I would expect some very small deviation in the case of not relying on Wilks' theorem. Normally it doesn't have such a huge impact. It's not that, I mean, obviously when you do the full analysis with the real data, it's important to see if it's like 1% or 1.2%. But I think the point we're trying to make is that we're really around the percent level. So like 0.1% up or down, it's not really going to depend only on this, but it might be also like some statistical fluctuation.
But you are looking to 1% effects. So if your statistical method produces deviations of that order, then my question is how reliable those results are.
I think, yeah, I would have to have a look at, I mean, the only way to know really what the impact is to do it. But I don't see any reason why Wilks' theorem would not very approximately hold.
I mean, for sterile neutrinos, it is known that it kind of cracks, right? So, and you can get off by more than 1%.
Yeah.
So I'm just wondering about how much that applies to NSI.
I think in the case of NSI, it's still quite robust.
Okay. And then a last question, if I'm allowed for that.
Yeah, sure.
Yeah. Okay. So you, at some point, you have to stick to high metallicity or low metallicity standard solar models.
Yeah.
How much the results vary depending on your choice?
So I think the overall, I mean, the solar parameters are basically going to be fixed by JUNO. So the determination of the solar oscillation parameters are not going to be highly impacted by this. When it comes to non-standard interactions, it is true that it's very sensitive to the density in the production points. So there might be an effect in there. That is true. So yes, there's going to be a difference whether it's the true model is like high metallicity or low metallicity. But it's also like you also have to average over the production region, and somehow some of these in principle big issues can somehow balance or wash out slightly. So I wouldn't expect it to really back down the change very substantially the results.
Okay, thank you.
You're welcome.
Is there any other question for this part? I don't.
Otherwise, we can move, and if there are more questions, I can answer in the end.
Yeah, please go on, Pablo. Thanks.
Yeah. So the second thing I wanted to discuss, it won't take long, I hope, is non-standard interactions with electrons from cosmology. So if we have additional interactions between neutrinos and electrons, the picture of neutrino decoupling can change. And so since we're going to have increasingly accurate measurements from CMB in the future, we can use those to constrain non-standard interactions. And that's the take-home message of this second part. So the picture of neutrino decoupling is that early in the universe, neutrinos are coupled to the constant plasma through big interactions with electrons. And at some point, so at around 1 MeV, these weak interactions stop being effective and neutrinos decouple from electrons and photons that are still in contact through production and annihilations. And then at lower temperatures, so later in the history of the universe, that temperature reaches a point at which two pairs of photons cannot create an electron-positron pair, but it's only electrons and positrons annihilating into photons that can happen. And so at this point, there's some entropy transfer to the photons. So this is the general picture, but it's actually a bit more complicated. It's not like at 1 MeV weak interactions stop being effective, but it's a continuous process. And it's also not like at 5.1 MeV electron-positron is the only process allowed, but it's also like a continuous. So the overall calculations or the overall picture is slightly more complicated. But the idea is that when first there's weak interactions that stop being effective and neutrinos decoupling, and then at some point one has electron-positron annihilation. Okay, and then an even lower temperature. So when a temperature is smaller than the mass of the electron, then the cosmological radiation density is given by this. So it's the density in form of photons plus the density in form of relativistic neutrinos and other species that you might have that we won't be considering them. So if you have some BSM or ultra-relativistic particle, then this will also contribute to the radiation density. And this radiation density can be expressed in terms of density of photons and parameterized with this N effective, which is what we call the effective number of relativistic species or effective number of neutrinos. So we know in the standard model we have 3 active neutrinos. So one would naively think, okay, then N effective equals 3, and that's it. It's a bit more complicated than that because, as I told you, the decoupling is not an instantaneous process, nor is electron-positron annihilation. One also has finite temperature QED corrections, and also neutrino oscillations have to be taken into account. So doing this calculation is quite complicated, but it has been done for 2 different groups of people, and the result is this one. So N effective is 3.044 plus minus 0.0002. So it's an incredibly accurate prediction. And it's exactly the same results for the 2 groups, independent groups. So it's a reliable calculation. And so we know what can we expect for an effective in the standard model. And if we happen to find a different value, then what's going on? So deviations can indicate either we have some additional degree of freedom, as I said before, so some relativistic degree of freedom, so some beyond standard model relativistic particle. And we can also have new physics in the neutrino sector apart from oscillations, and we weren't taking it into account. So for instance, non-standard interactions between neutrinos and electrons can lead to deviations in N effective, and this is what we check for. If we have NSI, we already know that oscillations are modified, but in the case of the neutrino decoupling, this is a superheating effect. So we don't expect this to be relevant almost at all. But it's also true, as I told you, that the decoupling is basically due to the fact that neutrinos interact with electrons. So if we have additional interactions between neutrinos and electrons, then this can be the decoupling can be either delayed or well, it can happen slightly before, depending on these non-standard interactions. To better understand what happens there is we know our cross sections for interactions between neutrinos and electrons are parameterized in terms of the standard model coefficients TL squared, DR squared, or coarse terms G and DR. And in the presence of NSI with electrons, what happens is that these coefficients are effectively shifted. So we have a contribution that sums with the GLs and GRs. For non-universal, so this means non-universal, neutral current, non-standard interactions with electrons can enhance or suppress the interactions that the interaction rate we will expect from the standard model, and flavor changing NSI can only enhance the interactions between neutrinos and electrons from a cosmic class. At this point, I have to shortly do some technical comments. So for this, we use the code that's called for the piano to compute the evolution. We also take into account the oscillation parameters from global fits, although the exact desired value of the oscillation parameters will not be that relevant for our study. And what motivated us to do this calculation is the fact that to future CMB observations from Simon's Observatory and CMBS4 projects are expected to have incredibly good sensitivity to the value of an effective. So in the best case, 1 sigma deviation of an effective is expected to be 0.02. So it is a very accurate measurement of an effective. And so we studied how an effective varies when one allows have non-standard interactions, and this is summarized here. So in the y-axis, you can see the value of an effective, how it changes with the epsilon for non-universal NSI. So we said non-universal NSI can cancel out standard model interactions. This would mean that there will be smaller or less interactions between neutrinos and electrons, and then the decoupling would happen earlier. This would lead to a smaller NSI. Or they can work the other way around. They can enhance the interactions between neutrinos and electrons with respect to the standard model, and this manifests as a delayed decoupling of neutrinos, so a larger N effective. So in this figure here, as I said, you can see how N effective varies when one changes the value of one of the NSI parameters, epsilon tau tau or epsilon EE. The color vertical bands are the limits we have from terrestrial experiments, and the dashed gray band is the limited future cosmological observations with set. So you can see they're very well constrained from terrestrial experiments, but we will have, for instance, here some bound on epsilon tau tau from cosmology. We know at one signal level, it cannot be any smaller than 0.75, for instance. Okay, so it's not really competitive, but it's interesting to see that cosmology can actually set bounds on NSI. Another case is flavor changing NSI. And as I say, they can only enhance interactions between neutrinos and the cosmic plasma because there are no flavor changing neutral current interactions in the standard model. So what happens is that whenever you have a non-zero NSI, then the decoupling is delayed and you end up with a larger N effective. So again, the color band is the limit from terrestrial experiments, and you can see that at one signal level, the cosmological bounds are not doing so bad. Okay, so it is somewhere here. So okay, it's not really competitive with what we have now, but it's a really interesting and complementary proof of the overall picture. One can also study what happens when one allows to have two different non-zero NSI. And this is one example that we studied. So for instance, you can see here different values of epsilon EE and here epsilon E tau. So one is non-universal and one is flavor changing. And the white bands are the limits from terrestrial experiments. Consider that there's only one non-zero parameter, and the white dot is the best fit point from the value predicted for an effective from the standard model. And the lines you see are isocontours of an effective. So it means along this line, an effective is, for instance, a 3.0 or 52. So let us see, for instance, what happens in the future, what can happen in the future. So we determine an effective to be this is the value 3.044, and from cosmology from CMBS4 we have an error of 0.02. So that means we know it's less than 3.64. So all this region is allowed. The region enclosed by this purple pinkish line, and everything outside this will be excluded by cosmology. So we are going to start setting constraints on NSI also from cosmology. The bounds again are not as good as from terrestrial experiments, but in some cases they're complementary. So this is just a different combination that I wanted to show because it's really the one that shows the best complementarity. It's epsilon tau tau and epsilon E tau. And again, as I said, everything inside the 3.64 or 64 region will be allowed by cosmology, but everything outside will be excluded. One signal, okay, still excluded or not favored. So in this case, the limits from cosmology are not so far from the terrestrial limits. And here there's another important thing to notice. The limits for terrestrial experiments that I'm showing considers only one NSI parameter is non-zero. Doing fits to scattering data with many different non-zero NSI parameters is complicated, and it's not normally done. Also to other data sets, we don't normally consider more than two to be different from 0, but in most of the cases we just assume one of the parameters is non-zero. But there can be funny deteriorances between them. And in cosmology, we can have some complementary directions to look at. So for instance, this combination here is very difficult to prove because to do so, one would need to do scattering of tau neutrinos on electrons. And we don't have a beam of tau, artificial beam of tau neutrinos to scatter on electrons. So we cannot really prove this particular combination, but cosmology can. Okay, so in this sense, it's complementary. And yeah, to finish, I just wanted to tell you that this part, the idea was that non-standard interactions, they modified the decoupling of neutrinos in the early universe. And so from CMB observations, we can set constraints on those. And I know I'm really out of time. I'm really sorry about this. So some final thoughts is just non-standard interactions are interesting from a theory point of view, but also they have regions as phenol. And so I show you, for instance, in the case of non-standard interactions with quarks, JUNO and Hyper-Kamiokande are going to provide some interesting limits on NSI while measuring oscillations very precisely. And we can also learn, for instance, about non-standard interactions with electrons from cosmology because they also play a role in the neutrino decoupling. So thank you very much. And I'm really sorry for being out of time. But I'm really, really happy to take questions and hope it was clear.
Don't worry, Pablo, it was fine. Many thanks for your talk. It was very nice. So is there any questions from the audience? Please raise your hand. Diego, go ahead.
Yeah, no, I'm sorry. Yeah, thank you.
No, I'm really happy you're asking questions.
Yeah, so there is so neutrino decoupling happens later than BBN. You are not considering constraints on BBN as far as I understand, because you are coupling only to electrons. So your NSI doesn't involve quarks.
Yeah.
But the same operator that couples to electrons can induce coupling to quarks at order D Fermi. It is true that the operator is suppressed, but predictions or measurements from BBN are rather precise. So how much these results are affected by the constraints implied by BBN?
So that's actually a very good question because I hadn't thought about it. Again, I know constraints from BBN are quite good in terms of charge current processes. So for instance, like inverse beta decay can actually alter the proton to neutron ratio quite a lot. So if you have some charge current NSI, this actually is relevant. But I don't know in the case of neutral current NSI. I'm not aware of what are the limits from BBN. So I would really have to have a look at them and compare them because yeah, there's some suppression, but I don't know how large. But yeah, this is actually a good question.
Yeah, I just was wondering that the diagram in which, I mean, you can close the two neutrino external legs into a loop and couple that to a set, and then the set couples to QQ bar. That will produce a diagram which is QQ bar E plus E minus, and that is certainly a process that will affect BBN. Of course, it's suppressed compared to the ones you are considering because your process is BNNSI are order G Fermi, while the one I have in mind is order G Fermi squared. So it's kind of suppressed, but you know, BBN predictions are rather stringent. Yeah. Okay. Now the other point which I would like to ask you is about my understanding is the following. So when you study neutrino decoupling, so there are two ways through which you can affect the process. I mean the whole decoupling. One is by changing the collision term in the Boltzmann equation level. The other one will be changing cosmology, you know, changing the expansion rate somehow, which why not? Okay. But there are scenarios in which, for example, if you have dark matter coupling to neutrinos, you will also have, you know, an impact on an effective. So if I have a measurement which has produces a number which is in the region that you pointed out and which you can test NSI, how do I know that what I'm getting is NSI and not in a scenario in which dark matter is coupling to the neutrinos or to the electrons?
Only from cosmology you cannot know. Only from cosmology only you cannot know, but you have some complementary probes. Like you have bounds on all those scenarios. So from inside you have many bounds from terrestrial experiments, and you can test that. So you can actually, if you really have some hints, you can do some really in-depth analysis and see whether on terrestrial experiments you can exclude the NSI that you would need. But only from cosmology you cannot distinguish.
Okay.
I mean, you can rule out, but you cannot really. It's not like a smoking gun signal.
Yeah, you can basically close certain parameter space, but you cannot point towards a physics which is responsible for a deviation.
Yeah, you can just.
Okay. May I ask a final question, which is kind of unrelated somehow? So there is this network of Boltzmann equations written by Scribano a couple of years ago. I don't know whether you're aware of that, because no, sorry, by Scudero.
Yeah.
Yeah. So the codes that you pointed to are codes which are rather involved. They involve these QED corrections and so on. The network of Boltzmann equations written by Scudero are rather friendly, so to say, and they seem to me that they are in agreement with what these complicated codes produce. Do you have an idea of how reliable those Boltzmann equations written by this guy are?
It depends. It depends on the precisions you want. I mean, it's reliable, but it's not as precise. So the thing is, these codes here I showed you, it's got like an error on the 4 decimal point from unaffected. So you can really go very, very precise with that. Whereas with the other Boltzmann equations are more simple. They can probably give an estimate that's more than good enough for most of the physics you can do right now with the unaffected you get from Planck. There's a chance that also from in future CMB determination of an effect. But if you really want to do something precise, or if the observations get really precise, then this code is not obsolete. Also, this code does not account for everything. So, for instance, I'm quite sure it does not account for neutrino oscillations.
No,
so
it doesn't.
If you really want to do some new physics that alters oscillations, if the impact on oscillations is small, you can in principle rely, but you're not being fully consistent. So you cannot do you can do this with NSI because the main contribution comes from the collision terms, but it's true that you're missing part of the physics because you're not included the impact of NSI on the propagation and oscillations there.
Okay. Thank you very much, Pablo.
Yeah, you're welcome.
Is there any other question from the ones that are still here? Okay, I think not. So Pablo, again, many thanks for the seminar. It was really nice. Jacinto says, very nice talk, congrats. So thanks a lot also to the people that come today, and see you next Thursday then, okay?
Yes.
Bye-bye.
Thank you. Ciao.